on fundamentals of mixed signals and sensors. So for today, we will be talking about analog to digital conversion or yung ADC. So pang pito na to dun sa ating mga lessons. So kung gusto niyo balikan yung mga previous lessons natin, tignan niyo na lang diyan. So ano yung mga pag-uusapan natin sa ADC? Una, we'll talk about yung analog signals and measurements. Ano ba yung pinagdadaanan natin? Bakit natin kailangan ng analog to digital conversion? Pangalawa, we will discuss ano ang accuracy, precision, and resolution. And anong kinalaman nito sa analog to digital conversion. Okay. And then third, we will discuss ano ang sampling theorem and ano ang nagiging purpose kung bakit kailangan natin itong sampling theorem na to. And then of course, merong limits ang ating measurements. Kaya naman, yun yung fourth discussion natin, limits on signal measurements. Then we will go on to the principle of analog to digital conversion. Okay. First, we will discuss yung quantization error, and then we will go on to some circuits kung paano natin ini-implement ang conversion from analog to digital signals. Okay? So may mga circuits tayo dito, mga common circuits that are used to convert analog to digital signals. Okay? So let's start by uh, some introduction no kung bakit meron itong ADC. So nearly all electronic systems, they deal with forms of energy katulad ng voltage, current, power, light intensity, and so on. So itong mga to, they change with time. So itong changes na tinutukoy natin to, these represent information about significant quantities or events na um, nagkakaroon ng interaction dun sa systems na tinutukoy natin. Okay? So kahit pa gaano kasimple yung ating system, meron yan tatlong main features. No? Katulad din ng mga more complex systems, meron yan tatlo. We have an input, okay? To that system, we have a processing stage and we have an output. So itong tatlo na to, napaka-importante na palaging meron yan sa isang system, input, processing, and output. So signals are uh, signals are derived from the real world outside sa mga electronic systems na meron dalawang klase. Meron tayong tinatawag na real-time information and information storage. Ibig sabihin ng real-time information, ito yung katulad ng mga nasasagap natin through switches, microphones, mga digital camera chips, di ba? Yan yung real-time information systems. Yan namang information storage systems, yun yung mga data na nakastore sa hard drives, sa memory chips, no? So, dalawang klase yan. Ngayon, yung itong mga information na to katulad ng real time, usually they are analog in nature. And of course, pag meron tayong analog na mga signals, kalimitan we interface them with the digital systems through an analog to digital converters, no? So, yan yung nandito sa ating first figure. Okay? So in this figure, we have uh, an analog signal from, for example, a sensor that is amplified to a certain level bago yan pumasok dun sa ating sampling and hold no circuit. So itong sampling and hold circuit, ito mismo yung nagbabago dun sa ating analog signal papunta sa isang sampled analog signal na siya namang papasok dun sa ating ADC o yung ating analog to digital converter. So itong circuit na to, yung ating ADC, dito natin kino-convert into digital form, papasok sa ating CPU. No? Yung mga processing units natin, pagka meron tayong isang, let's say for example, mga embedded systems. Okay? So, napaka-importante na kabisaduhin natin ito. Kasi itong figure na to, this represents yung ah, mga embedded systems na ginagalawan natin bilang mga electronics engineers and computer engineers. Ganito yung basic principles. Kung matatandaan nyo to by heart, mas maganda. Okay? So, this is for analog to digital conversion. No? Meron din sa output side o yung after ng processing system, meron din tayong digital to analog converter. Kung paminsan kasi, it is required or necessary. Paminsan necessary na yung ating output signal binabalik natin sa analog, no? So meron din tayong mga circuits that do this function ng analog to digital to analog conversion. Pero sa ngayon, itong discussion natin will focus on analog to digital conversion. Okay? So the way signals are produced and processed in these kinds of electronic systems, medyo nagbago na siya over time. Although hindi naman ganun kalaki kagaya ng iniisip nyong pag-improve. No? As a matter of statistics, majority ng mga electronic signals ngayon are in digital form. Meaning, yung interpretation involves yung mga one and zeros of the digital technology. Bakit? It is mainly because digital signal processing and related digital technologies uh, are more powerful and flexible, tsaka mas maganda yung performance nila kumpara sa mga analog signal processing counterparts. So, kung nag-exist pa yung mga analog signal processing na yon. So, maraming routine digital processes today cannot be performed gamit yung mga analog systems only, no? Kahit pa kaano yan ka-elaborate or gaano pa yan kamahal. Kaya naman, importante na alam natin itong pagko-convert ng analog to digital kasi ma-experience natin yan sa field na kakailanganin natin talaga siya. So part ng fundamentals of mixed signals and sensors yung pag-aaral ng conversion from analog to digital systems. Okay? So kanina pa natin pinag-uusapan ang analog and digital. Balikan muna natin, ano ba ang isang analog signals, no? Or analog signal and paano yan minimeasure? So yung isang analog signal, yan, okay? An analog signal is a form of electrical energy, pwede yang voltage, pwede yang current or electromagnetic power for which there is a linear relationship between the electrical quantity and the value that the signal represents. For example, uh, let's say telepono o kaya microphone signal. Okay? There is a direct proportion between the instantaneous sound pressure habang nagsasalita tayo sa microphone and yung kanyang output voltage. So, ganun din siya. Yung ating mga analog signals, they are usually in time domain pagka uh, nire-represent, no? Um, Real analog systems can show distortion and noise. Okay? Inherent yan sa mga analog systems. Meron talaga siyang distortion at noise. So parehas, maaaring na-discuss niyo na yan sa mga previous subjects ninyo. Ang importante or ang gusto nating bigyan ng emphasis sa ngayon, merong effect, okay? Yung distortion and noise na pwede nating makonsider na nag-a-add or nagsusubtract ng isang quantity dun sa ating ideal voltage. Okay, so hindi na nagiging perfect yung ating signal or yung analog signal. In this particular scenario, nagkakaroon na tayo ng tinatawag nating error, no? Usually yung error nanggagaling yan pag meron tayong mga noise kung saan-saan, no? Tulad din sa sensor, meron tayong noise, yung mismong signal merong noise, yung amplifier natin imperfect, meron din siyang noise. And bago pa man pumasok yan sa ating digitizer, yung sample and hold, meron pa rin tayong mga na-experience na mga noise dyan. So, etong noise na to, pumapasok yan or sumasama at nagsusubtract yan dun sa ating signal, kaya nagkakaroon tayo ng tinatawag na error. Okay? So itong error na to, na-amplify to. Kung bago pumasok ng amplifier, na-amplify siya. So pag sinabi nating absolute error, no? For example, ito yung mga tinatawag natin measurement sa analog signals. Pag sinabi nating absolute error, ito yung difference, no? Nung ating actual voltage or yung actual signal tsaka yung ating ideal, no? Ideal, ito sana yung gusto nating output. Kaya lang, nahaluan kasi siya ng noise, kaya nagkakaroon tayo ng absolute error. In some disciplines, usually, kinukuha na lang natin yung tinatawag nating relative error. No? Ano ba yung relative error na yan? Okay. So itong relative error, it is a dimensionless number na nakukuha natin by dividing the absolute error by the uh, through error-free quantity. Ibig sabihin, yun yung ating absolute error divided by yung ating true value or yung ating ideal output. Okay, so diyan natin nakukuha yung ating relative error. Bakit ba natin pinag-uusapan itong mga error-error na ito, no? Kasi napaka-importante na kapag nagko-convert tayo ng mga analog to digital signals, importante na ma-measure natin yung error or gaano ka-accurate yung ating uh, conversion, right? So, diyan kasi magbabase kung gaano ka-effective yung ating ginawang conversion. Okay? So kaya naman, bago tayo pumunta sa main discussion natin, pasadahan natin ang discussion about accuracy, precision, and resolution. So, uh, bilang nandito tayo sa analog to digital conversion, let me just refresh you on the definition ng accuracy. So, accuracy refers to how close a measured quantity is to its true value. Let's say nagta-target tayo ng 100 sa exam, pero ang nakukuha natin 80. So, napakalayo natin doon sa target nating 100. Malayo tayo ng 20 points. So, yun ang principle ng or yun ang concept ng accuracy. Okay, again, accuracy refers to how close a measured quantity is to its true value. Okay? So, ganyan siya. So, for example, ito, meron tayong apat na illustration dito. Masasabi natin kung ang target natin itong nasa bullseye, masasabi natin itong first illustration natin is less accurate kumpara dito sa pangalawa dahil mas malalapit yung uh, hit nung nasa second illustration, no? Pero masasabi naman natin na mataas yung accuracy at kung katulad siya nitong nasa pang-apat na uh, illustration, no? Bullseye talaga siya. Okay, so yung accuracy, pwede nating i-represent or illustrate ng mga ganitong examples. So, ano naman ang tinatawag nating precision? No, minsan kasi nakakalito itong dalawa na ito. So, sabi natin, accuracy refers to how close yung ating measured quantities is to its true value. Okay? Ang precision naman, so, ang precision, it is independent of the true value of the measured quantity. Instead, precision refers to how repeatable a measurement is. Okay? That is, how much variation occurs from one measurement to the next measurement. Usually, it is considered over a sequence of several measurements. So, ibig sabihin, pag inulit-ulit mo daw yung iyong uh, pagme-measure, gaano kalalapit itong mga measurements mo. So, ito, sa una nating illustration, napakaganda ng precision niya. No? Kasi dikit-dikit yung magkakasunod na arrow, no? Kung saan naglanding yung kanyang arrows. Sa pangalawa, medyo less precise siya kasi medyo may malalayo yung agwat ng kanilang distances. Sa pangatlo, napaka worse, no? Medyo worse yung precision dito dahil talagang hindi mo ma-describe yung kanyang pwesto. Pero sa pang-apat, maganda rin yung kanyang precision dahil dikit-dikit yung iyong measured values. Okay? So speaking of accuracy and precision, we can actually illustrate yung concept ng accuracy and precision using this examples. So dito sa una, uh, precise siya, no? Precise pero hindi siya accurate. Okay, so napakalayo niya dun sa kanyang target. Sa pangalawa naman, medyo accurate siya, di ba? Medyo tanggapin natin yung accuracy niya, pero hindi naman siya precise. Sa pangatlo naman, so hindi siya precise, hindi siya accurate, di ba? Hindi rin siya accurate. Yan. Then sa pang-apat, ito yung best case. Okay? So, accurate na siya and then precise pa. We want that our system or yung ating analog to digital conversion na magiging ganito yung ating result. Kapag kapag kinonvert natin yung analog to digital at ibinalik natin doon sa analog, dapat precise siya and accurate. Okay? So, merong pangatlong term, yung tinatawag natin resolution, medyo related siya sa precision. Okay? So, sinasabi natin na yung resolution, it is the smallest physical change in the measured quantity that will produce a corresponding change in the measurement. So, ang resolution, para lang mas madali yung maalala, kung meron kayong digital multimeter, so, kung gaano karami yung iyong decimal points, yun yung iyong resolution, no? So, katulad dito sa una, 1.2, di ba? Dito sa illustration natin, pag tinaasan mo yung resolution mo, naging 2 decimal limits ka na, decimal points ka na, pwedeng yung iyong measurement mas magiging precise or mas accurate kasi tinaasan mo yung iyong resolution, no? Naging 1.23 na siya. Pag dinagdagan mo pa yung decimal points, maaring mas magiging accurate na siya at maging precise dahil natutumbok mo na yung pangatlong decimal point. Okay, so ganyan lang siya. So, resolution refers to the smallest physical change in the measured quantity that will produce a corresponding change in the measurement. Okay? Yeah. Yan. So dito naman tayo sa digital signals and concept ng sampling theorem. So in contrast to an analog signal na pwede naman nating i-represent mathematically as a function of time, itong mga digital signals are invariably expressed as discrete numbers called samples. No? Ito yung netong nasa red figures natin or red lines, ito yung ating mga discrete time signals. Okay? Yun yung tinatawag nating samples. Okay? So for simplicity, we will assume that the sampling times are evenly spaced. No? So equal periods kung kailan sila kinuha ng sample, yan. Para mas ma-illustrate pa natin yung concept ng sampling, so let's say meron tayong sine wave na voltage, tapos ang amplitude niya ay 1 volt, no? So let's say ganyan, 1 volt. So, meron tayong 1 volt diyan. Tapos meron siyang frequency na let's say 500 hertz. Yan. So itong sine wave na to na may frequency ng 500 hertz, supposedly sasample natin siya for conversion papunta ng digital form. No? Kung ang kukunin nating, so drawing tayo ng signal dito, no? Kung ang kukunin nating sampling interval o yung layo ng mga samples, mga succeeding samples is let's say ano siya, 500 microseconds. Sample lang naman, no? Let's say yung period or sampling time is 500 microseconds. So ano ibig sabihin niyan? Ang ibig sabihin niyan, kada cycle ng sine wave, kukuha ka ng uh, apat na samples kada cycle ng sine wave. Okay? Kasi yung ratio ng sine waves period, di ba? So let's say meron tayong frequency no na 500 hertz, tapos meron tayong sampling na 500 microseconds. Yung period ng ating isang cycle ng 500 hertz, that is 1 over 500, right? And that will become equal to 2 milliseconds. Ibig sabihin, sa buong cycle ng ating sine wave, equal yan sa 2 milliseconds. So, itong unang kalahati, 1 millisecond. Itong pangalawang kalahati, 1 millisecond din yan. So, pag ginati pa natin, ito na yung 500, no? 500 microsecond dito, kukuha tayo ng sample dito, tapos dito naman another 500 microseconds, then another 500 microseconds ulit, then another 500 microseconds din dyan. So in this case, kada isang cycle ng ating 500 Hz, equal yan sa apat na sample. So, ganyan yung pagsasample natin, no? So the result of these four sampling operations, tinatawag natin yung ordered pair of numbers. Yung first number represents the time at which the sample was taken, and then yung second naman kung ano yung voltage at that time, no? So for let's say ito dito sa unang sample natin, no? Say ito 0, ito yung 1, ito yung 2, 3 and 4. Kung ano yung voltage na makukuha niyo diyan, yun yung first sample, yun yung sample mo. So 1, and sa unang sample 1 and let's say 1. Sa second sample, you have 2 and then 0. Sa third sample, let's say you have 3 and negative 1. Then sa fourth sample, you have 0 ulit. Okay? So, ganun lang siya. Okay? So, positive 1 volts, 0 volts, negative 1 volts, and then 0 volts. So, the reason yung mga digital systems na kailangan nilang i-perform yung periodic sampling rather than dealing with continuous voltage directly kasi uh, lahat or karamihan ng mga digital systems, kahit gaano pa yan ka-complex, they incorporate yung mga tinatawag nating clock, no? Meron tayong tinatawag na clock. And itong clock na to, ito yung nagde-determine ng maximum rate at which a continuous input signal can be translated into discrete numbers. So yan, let's say you have 500 megahertz, di ba? So let's say yun yung maximum rate or yung clock rate ng iyong computers or ng digital systems. So yan yung mag-determine. No? Although it is possible to perform conversion ng isang analog signal papunta sa digital form, in a way that reflects changes in the input almost instantaneously, representing these changes in numerical way presents problem to the system. Dahil nga yung clock frequency natin is magiging mas mabagal na siya kumpara dun sa maximum rate ng change ng iyong input signal. Ibig sabihin, you cannot sample a particular analog signal more than dun sa iyong clock rate. No? So, importanteng malaman natin yan. Kaya naman, uh, yung mga digital systems must generally sample analog signals at a rate that is considerably less than the highest frequency clock signal used in the system. So, if you have a system na 500 megahertz, so huwag ka magsasample ng 500 megahertz din, no? Kasi mahihirapan yung system mo. Okay? So, yan. There is there is an exact mathematical relationship between the highest frequency ng mga signal na pwede nating i-sample and the sampling frequency, no? Na required para ma-sample natin yung signal na yon. Okay? So yun yung tinatawag nating Nyquist sampling theorem. Anong sinasabi ng Nyquist sampling theorem? No? Nyquist. Nyquist sampling theorem. Anong sinasabi niyan? The theorem states that as long as the sampling frequency is more than, no? As long as the sampling frequency is greater than twice ng ating maximum frequency, di ba? Walang mawawala dun sa information. Okay? By converting the analog signal into a discrete time signal, basta yung iyong tawag dito, yung iyong sampling frequency is more than, no, or at least twice ng maximum frequency ng iyong analog signal. So usually, yan yung sinusundan natin na na sampling rate para dun sa ating ah, mga analog signals. Okay? So, for example, meron tayong signal na ang highest frequency component is, let's say, 500, no? 500 megahertz. So, dapat ang iyong sampling rate should be at least twice nitong 500, no? So, at least you have a sampling rate of greater than 1 gigahertz. Yan, mga ganyan. No? And of course, kung yung sampling rate mo eh 1 gigahertz, dapat yung clock rate mo mas mataas doon. Kasi para hindi mahirapan yung iyong system. Okay? So, usually, hindi naman natin sinasakto na times 2 yung ating sampling rate. Minsan gumagawa tayo ng tinatawag nating oversampling. Katulad ng neto. Ng first illustration natin, yung ating ratio ng sampling rate doon sa ating maximum frequency is 2.6, no? Mas mataas pa siya sa 2. Ganito yung itsura niya. Okay? There are some advantages of doing yung tinatawag nating oversampling. Of course, that is sampling at a higher rate than strictly required by the theorem. Okay? So, however, it is enough to know that sampling a band-limited signal can be preserved as long as the sampling rate exceeds the maximum rate prescribed by the sampling theorem. So, ganyan yung itsura niya kapag nag 2.6 na yung ratio ng iyong ah, sampling rate to the maximum signal. No? Pagka 2 naman, ganyan siya. So, sa 2 pa lang, medyo okay-okay na tayo dyan. Pero, may mga times na gumagamit tayo ng mga sampling rate na mas mababa dun sa pine-prescribe ng theorem. No? Less than 2. Ito yung tinatawag nating undersampling. No? Yan. Pag sinabi nating undersampling, binabiolate natin yung theorem, no? Sometimes merong ano yan, tawag dyan, advantage and disadvantage. Yung isang case, meron tayong tinatawag na undesirable effect na tinatawag nating aliasing. Okay? So, aliasing. Okay? Aliasing. So, itong aliasing na to, uh, ito yung effect niya, no? Nagpapansinin niyo tong green line na to, nagiging parang low frequency yung ating signal or yung ating tawag dyan, output, no? Kaya naman ang tinatawag natin yung undesirable effect. Okay? So sampling can be considered mathematically as multiplication ng mga periodic pulse at the sampling frequency. So kapag yung ating sampling rate, no, is mas mababa dun sa ating uh, sinasuggest ng ang tawag dito, ng Nyquist theorem, yung ating frequency components, no, from the original baseband signal and the lower sideband, they appear in the same frequency range. So ibig sabihin, parang under an alias, no, nagkakaroon ng spurious in the sense that they are products of the sampling process and were not present in the original signal. So ayaw natin 'yan. Although, no, medyo mahirap kasing i-eliminate yang aliasing na yan by filtering. Consequently, itong mga undersampled signal will contain alias signals that appear as erratic noise and distortion. Depending on the spectral content ng original signal, uh, itong aliasing effect almost always undesirable yan. And is the main reason kung bakit dapat hindi tayo nag-undersample ng mga signals. Okay? So, pagdating sa principle ng analog to digital conversion, iniiwasan natin ito na i-undersample yung ating signal. Kaya naman, importante na tatandaan natin yung tinatawag nating Nyquist sampling theorem. Again, it states that na pag sinundan natin yung ating sampling rate that at should be at least twice ng ating maximum frequency content ng ating signal, walang mawawala dun sa ating information kahit na i-convert pa natin into digital yung ating signal. Okay? So, yan. Although, pwede naman tayo talagang gumamit ng napakataas na sampling rate dun sa ating signal. Okay? Of course, it is possible in principle na gawin yon. Pero kahit gaano pa kapino yung ating time scale na gamitin, meron pa ring limit dun sa resolution ng ating analog system. Okay? Ibig sabihin, ah nagkakaroon pa rin talaga yan ng discrete or quantum nature dun sa ating mga analog signals. Okay? So, bago tayo pumunta rin sa mga circuits, pasadahan natin itong tinatawag nating shock noise. No? Ito yung minsan naglilimit dun sa ating uh, analog to digital systems or conversion systems. No? So, yung shock noise, it arises from the discrete nature of electrons. So, meron tayong illustration dito, kung mapapansin niyo parang sine wave siya. Pero pag i-zoom nyo ng i-zoom yan, no, para makikita nyo mga dot-dot. Okay? If you examine an analog record of current flow closely enough, may makikita kayo na mga series of pulses, each of which represents a single electron. So, ito yung naglilimit dun sa tawag ito, sa maximum frequency na pwede natin gamitin. Okay? So, ang punto ng ating pagdadaan dito sa shot noise is actually to show that the traditional distinction between analog and digital systems are more apparent than real. Okay? Nevertheless, marami dun sa mga signals uh, are easily acquired or transmitted in the analog form. And of course, it is therefore necessary to convert this analog signal papunta sa mga digital signals and vice versa. Digital representation papunta sa analog. Okay? So, ayan. As a basic discussion sa mga analog to digital signal, pasadahan natin itong tinatawag nating quantization noise. Okay? Or quantization error. Ano ba yung quantization error na yan? So, diniscuss na natin yung isang band-limited analog signal, pwede natin i-reconstruct from samples, di ba? Basta tama yung ating sampling rate, according dun sa theorem, Nyquist theorem. Yung sampling by itself is not inherently digital operation. Di ba? Gumagamit pa rin talaga tayo dyan ng mga analog circuits para ma-convert yung ating dito, yung analog signal papunta sa digital numbers. Okay? Pero, however, itong procedure na to is actually to first sample an analog signal at a particular sampling frequency. And pag ginagawa natin yon, panigurado, meron tayong tinatawag na quantization error. Okay? So, nag-a-arise itong quantization error doon sa ating tinatawag na resolution. Kaya diniscuss natin yung resolution kanina. No? The resolution of an analog to digital converter or yung tinatawag nating ADC is related to the number of meaningful bits na kaya niyang i-produce. Okay? So, for example, itong ating nandirito, yan. Ito dito sa illustration, yung ating bits ay actually tatlo, no? Ibig sabihin hanggang 8 yan. Okay? So, 2 to the 3. So ito yung mga ating digital output, 0 hanggang 111. 000 hanggang 111. So kaya na yan ng 8. Okay? So kapag magsasample tayo ng isang signal and nag-represent tayo ng 8 output or meaningful, no? 3 meaningful bits. So syempre hindi naman lahat tatama diyan sa mga output na yan, no? Sakto. Hindi naman ganun ang analog signal. So dito sa illustration natin to the right, kung saan tatama yung sample, okay? Once na mag-sample tayo at saan siya tumama, yung pinakamalapit na tawag dyan, na digital output, yun yung pupuntahan niya, no? So for example, dito sa 0, tinamaan is 2.5, diyan siya sa 100. Sa second naman, oops, hindi siya umabot. Pero ang pinakamalapit sa kanya is yung 3.125 volts. Kaya naman yan ay 101. Sa third sample natin, uy, sakto. Di ba? 2.5, 100 yung kanyang output. Doon sa pang-apat, di ba? Hindi na naman ulit sumakto. Pero ang pinakamalapit sa kanya is 1.875, kaya naman 011 yung kanyang digital output. So yung napapansin ninyo ng mga variances between the original analog signal and yung quantized sampled signal, yan yung tinatawag natin mga digital or quantization error, no? Yan. Yung difference between those signals or those values, yun yung tinatawag natin quantization error. So, again, nakadepende yan dun sa ating number of meaningful bits. Mas maraming bits kang gamitin, mababa yung iyong uh, quantization error. Okay? So, again, this is a concept of resolution. Mas marami kang, 'di ba, sa resolution do sa multimeter kanina sa example, mas marami kang decimal point, mas eksakto yung measurement. Dito naman sa ADC, uh, mas marami kang bits na gamitin, mas maliit yung iyong quantization error. Of course, even if mataas na yung inyong bit or let's say 16 bits ka na, hindi pa rin talaga yan enough para ma-perfect na ma-represent yung iyong analog signal. Meron at meron pa rin talagang tinatawag tayong quantization error or what we call as quantization noise. Okay? So, kailangan lang i-minimize natin yan. And it turns out that kapag nag-oversample tayo, no, habang tinataasan natin yung ating sampling frequency, okay, we can move yung spectrum ng quantization noise around so as to minimize yung effect nyon sa final output. So, it is necessary na mag-sampling tayo according to the theorem, and pwede tayong magdagdag ng kaunting oversampling para ma-minimize natin yung effect ng quantization error. Okay? So, ganyan yung concept niya. Punta naman tayo dito sa concept na tinatawag nating sample and hold. Okay, ano ba itong sample and hold? So, oops, oops, oops. By now, medyo obvious na sa atin, di ba, na yung bandwidth ng signal na i-convert natin, yun yung magde-determine kung gaano dapat kabilis mag-operate yung ating ADC. So, according yan sa sampling theorem. And then, setting a oversampling. So, and as we have seen, how the number of meaningful bits that the ADC can deliver, ito yung tinatawag nating resolution, related to sa quantization error or noise introduced by the conversion process. Maraming klase or types ng ADC circuits, but most of them, kumbaga meron niyang main ingredients na common sa kanila. And at the heart of many ADC circuits you will find one or more comparators. So itong comparators na to, diniscuss na natin yan dun sa ating mga previous op-amp circuits, right? So a comparator is a hybrid analog digital circuit that can be thought of as an overdriven differential amplifier na yung output is actually pwedeng 0 or 1, right? So kino-compare lang naman niya eh. Then magre-release siya ng output uh, according doon. So itong sample and hold principle is actually ganun din yan, no? So nakikita nyo dyan sa example natin is a basic sample and hold circuit consists of a NMOS. Itong first example natin, NMOS transistor or yeah, tama. NMOS transistor and meron yung capacitor. Okay? Yung control input natin simply turn on the N-channel MOSFET for a very short period of time. Ito rin tinatawag nating sampling width. No? Habang naka-turn on yung N-channel MOSFET na yan, uh, ito yung time kung saan yung analog voltage level is stored at the capacitor. No? So, kinukuha niya yung voltage amplitude ng ating analog signal and then i-store niya dun sa capacitor. Di ba? Once na ma-charge na yan, according dun sa duration ng sampling width, i-release naman niya yung voltage na yan. So, yun yung ating quantized signal. No? So, again, ulit-ulit-ulit yan, according sa ating sampling theorem, then, yun na yung ating nagiging input. Input naman ngayon yan dun sa ating uh, processor. No? Quantized signal na siya. Okay? So, yan. Another this tawag ito, point to give about sample and hold circuits is dahil merong erratic result that can occur kapag merong mga raw unprocessed signal na finifeed natin directly papunta dun sa comparator. Yung comparator signal usually meron pa rin yan talagang sample and hold circuit. Okay? So ang function nito is to sample or track yung ating input signal at a definite time. And then hold, kaya siya tinawag na hold, sample and hold kasi sinasample natin siya tapos i-hold muna natin yung particular voltage na yon while the comparator examines it. Di ba? So habang chine-check ng comparator yan, naka-hold muna siya, naka-quarantine siya. And then, bago siya i-release ulit. Okay? So, makikita nyo dyan yung illustration ng ating uh, sample and hold. Meron tayong capacitor dyan, no? So, yun yung nagbibigay ng ating clock or yung sampling width. And then, i-store muna yan dyan bago yan i-compare, magiging sample signal na siya. Okay? So, ganyan lang siya. Napakasimple ng sample and hold operation. Yet, napaka-useful nito. Okay? So, yung susunod natin mga discussion or mga slides, yung discussion about mga basic analog to digital conversion circuits, meron niyang comparators and sample and hold circuits. Ito yung dalawa sa mga pinaka-importanting building blocks, no? Building blocks ng ADC architecture. And yung iba, yung ibang components na makikita ninyo, usually op-amps, integrators, mga filters, and some digital functions na kailangan para ma-implement yung operation ng isang analog to digital conversion. Okay? So, let's go to the first example ng ating ADC, no? Ito yung tinatawag nating flash ADC or yung tinatawag nating flash type ADC. Okay? So, ano ba yung flash type ADC na yan? Okay? So, yung nakikita niyong circuit na yan to the left, yung tinatawag nating 3-bit ADC. Bakit? Meron siyang 2 to the 3, no? 2 to the 3, which is 8 uh, operational amplifiers. No? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So kaya siya tinatawag na 3-bit ADC. Yung mga analog signal, they are applied sa lahat ng positive input or yung non-inverting. Okay? So, apply natin yan dyan. Okay? Tapos, yung reference voltage natin dito is distributed to each negative input terminal ng kada volt na ng kada op amp. Ibig sabihin, dinidivide natin yung voltage. Okay? So, anong ginagawa nito? Each operational amplifiers or amplifier, they act or it act as a differential amplifier and amplifies the difference between dito sa ating input tsaka dun sa ating reference signal. So, para mas maintindihan natin, let's say yung ating analog input dito sa output 7, pag yung voltage input is greater than 0, no? Then less than or greater than 0.625. So yung ating output ng 7, 0 yan, 0, 0, 0 din sa kada comparator, no? So ganyan lang naman siya. Pero once na yung ating analog signal is between 5 and 4.375, nagiging 111 na siya. Kasi nga, nagbabago-bago yung ating reference input or yung reference voltages. Gawa ng meron tayong uh, voltage divider network dito sa ating uh, inverting inputs. No? Yan. Kaya naman nagagawa natin gawing i-compare yung ating analog input, yung amplitude ng ating analog input dito sa pitong uh, values na yan. No? So in this case na yung comparator, kaya niyang magbigay ng 0 and 1 in which meron tayong flash ADC encoder na IC. Siya ngayon yung magsasabi kung ano yung magiging output, digital output ng analog na yan. No? So in this case, yung digital output niya is 000, 0001, 010, 011, ganun na siya. So yun ang basic principle ng flash ADC. No? Pakasimple lang siya. Okay? Next, ito naman meron tayong tinatawag na ramp ADC. So medyo iba na yung kanyang construction. Okay? So itong ramp ADC, gumagamit na lang siya ng isang operational amplifier. Hindi katulad ng flash ADC, marami, di ba? Dito naman, isa na lang yung ginagamit niya. Pero kapalit nung maraming op-amps kanina, it employs an up counter. Diba? Meron na siyang up counter. As well as a digital to analog converter in the loop. Meron na siyang up counter na let's say may output na dito, magsasabi dito, magsisignal, dagdagan mo na. Yung mag-count, mag plus 1 ka dito. So, ang operation nito, meron tayong analog input dito na sinasample and hold natin. Iko-compare yan dun sa ating output ng DAC. No? Then, yung output naman nito, it's either 1 or 0, papasok yan dun sa ating 4-bit counter. So, itong 4-bit counter, yan yung magbibigay ngayon. Yan natin kinukuha yung output natin. Okay? Yung 4 na yan. Pero, hindi doon natatapos. Babalik muna yan, magkakaroon yan ng loop. Okay? Pabalik dun sa ating digital to analog. Para naman pagkumparahan ulit ng susunod na analog signal. So, itong digital output natin, kinukuha yan dun sa ating terminal ng counter. And it progressively forms within the several clock periods. Hindi katulad nung sa flash ADC, instantaneous, di ba? Yung ating pagko-compare. Yan. So, yan lang naman ng operation ng isang ramp ADC. Meron tayong isa pang mas magandang construction or pagkaka-implement ng ADC. Ito naman yung tinatawag nating successive approximation type ng mga ADC. Ito yung pangatlo, no? Usually ito yung pinaka-common or ito yung pinaka-common sa lahat ng ADC. Okay? Itong third type na ADC na to is based on the successive approximation technique na ginagamit to estimate the value of an analog voltage. So, in this circuit, instead of using a 4-bit counter, gumagamit na tayo ng control logic to replace yung para ma-overcome yung mga disadvantage ng ramp ADC. So, tinalo niya yung flash type at saka ramp type kasi in terms of speed and the number of components used in the circuit. Dahil dito sa control logic na to. Uh, in this figure, meron tayong up counter, di ba? Meron pa rin tayong up counter in the ramp ADC, pero pinalitan lang natin yan na control logic na successively kino-converts yung analog input into digital form. Paano? By trial and error, no? So, yung output ganun pa rin naman dito pa rin kinukuha. Pero kaya nga siya tinawag na successive ina-approximate niya yung value ng magiging output niya. So medyo mabilis ito at less component yung kinagamit. Okay? So hindi ko na i-discuss yung ibang mga numbers na yan, no? Medyo common sense naman yan. Next is yung tinatawag nating sigma, diba? Delta sigma ADC. Ano ba yung delta sigma ADC na yan? As the name suggests, itong delta sigma ADC comes from the meanings ng Greek letters, no? Uh, Delta, ito yung Greek niya, tapos sigma, yan. No? Delta, sigma, ibig sabihin ng delta, difference, and then yung sigma naman, sum. Difference, sum, implying that the system operates on differences and sums. Okay. That is true as far as it goes, although yung details or the details are somewhat more involved. So, itong figure na nandito ngayon is a simplified form ng delta sigma ADC. Medyo masyadong simple ito, pero useful naman ito kasi dinidemonstrate niya lang naman yung basic principles na para mas malinaw sa atin yung yung principle ng delta sigma ADC. Although yung circuitry talaga niya is sophisticated in nature. Okay? So, yung delta sigma ADC, it has two parts. Okay? Meron tayong tinatawag na delta sigma modulator. Okay? It converts the analog input into a digital waveform. Okay? And a digital logic and control subsystem that converts the digital modulated output to a form suitable for further digital processing. So, yan. Ganito yung ano niya. So, let's consider meron tayong delta sigma modulator first. No? So, an input signal goes to a summing function. Okay? Ito yan. So, which in practice can be an op-amp connected as a differential amplifier. So, itong summing junctions output, pumapasok yan sa isang integrator circuit. So, itong integrator, di ba, na-discuss na rin natin yan. Again, typically, it can be implemented with an op-amp. Finally, itong analog output ng integrator, papasok yan sa non-inverting input ng isang comparator. Okay? Ngayon, ano ang ginagawa dito? Ini-invert yung inverting input naka-ground so that the comparator simply indicates whether yung integrator's output is less than or equal to 0. So, chinecheck lang niya kung less than or equal to 0 yan. Okay? Ngayon, ang output ng comparator is actually a digital signal na yan, di ba? It's 0 and 1. So, it is periodically sampled by a latch or yung tinatawag nating D-type na flip-flop. Okay, ito yan. D-type na flip-flop. So, itong klase ng flip-flop na to, it transfers whatever digital state na present dun sa D input, no? Papunta naman dun sa Q output upon the arrival of the rising edge ng clock pulse. So, ganun lang yung frequency ay yung operation ng isang flip-flop. So, when the comparator's output is transferred to the Q output ng flip-flop na yan, so it is sent both to the logic and control subsystem. Okay? And to the input of an analog switch. So, pabalik. Okay? So, magkakaroon tayo ngayon ng feedback doon sa uh, ating system. No? So, note that the output ng switch goes to the inverting input ng ating summing junction. No? Babalik siya ulit. So, ang tawag natin dito, again, is negative feedback connection. In the sense that yung positive input ng ating summing junction becomes a positive slope from the integrator which feeds the non-inverting input ng ating comparator. So, itong negative feedback na to, ibig sabihin lang yan, the system will constantly try to cancel out yung mga integrated effects ng ating input signal. Okay? By producing mga sequences pabalik dun sa ating uh, integrator. So napakaganda, no? Napakaganda ng ng pagkakakonstruct ng isang delta sigma ADC. Okay? Medyo sophisticated yung circuitry niya pero very effective. And then lastly, we have this uh, dual dual slope integration ADC. Ano ba yung dual slope integration ADC na yan? At the opposite end ng speed resolution spectrum from the fast but ratherly costly flash converter is the dual slope integration ADC. Itong dual slope integration is actually a slow method, no? Pero ang kagandahan dito sa dual slope integration is very very accurate yung kanyang result. Kaya naman uh, meron siyang special applications. No? So dito sa presentation natin, we have the block diagram ng isang dual slope integration ADC. So meron tayong voltage or input voltage ng ating signal. Okay. Connected yan sa isa sa mga terminal ng isang SPDT, electronic switch. Meron tayong switch dyan na SPDT. Tapos, connected yan sa uh, yung isang terminal na sa reference voltage. No? Uh, Tapos yung ating common, papasok ngayon yan sa ating integrator. Integrator din to guys, no? Yan. Integrator. Tapos yung output ulit niya, pupunta ulit ng comparator, papasok sa control, logic and control. And then, ang output ng ating logic and control, magiging feedback ulit yan. Pabalik dun sa ating electronic switch. Ngayon, itong output, siya yung nagko-control dun sa switch and measures the time intervals with reference to an internal clock signal. So, ganoon lang ang function niya. Wala siyang halos pinakaiba sa Delta Sigma ADC. No? Pero napaka-accurate nitong result na ito. Itong circuitry na to. Okay? So marami pang klase ng ADC approaches, no, na hindi ko na i-discuss dito. I will discuss it on some other presentations. Marami pa. But then these are the most common types of ADC circuits, from the flash type, the ramp type, successive approximation, we have the delta sigma and the dual slope integration ADC. So that's it. That's about it. Para sa lesson natin on analog to digital conversion. on the fundamentals of mixed signals and sensors. I hope meron kayong natutunan dito sa lesson natin na to. Next up, we will discuss digital to analog conversion naman. No? And maraming salamat sa pakikinig. Stay safe everyone. Have a nice day.